This presentation is delivered by the Stanford Center for Professional Development.
Okay. So today we're gonna go through optimization problems. I mean, the first part is a bit boring. It's just setting down basic terminology like what does it mean to be feasible? What are the constraint sets? Actually, what is a convex optimization problem? But then it will transition to actually useful. So you actually find out about what a linear program is, what a quadratic program is, second order cone program, and these types of things. And we'll get to those maybe later, hopefully this lecture. So we'll start with just the boring nomenclature of an optimization problem. So an optimization problem looks like this. This is a notation for it, is to minimize an objective, f0 of x, subject to fi of x less than 0. That's from I equals 1 to m, and hi of x equals 0. So this is sort of a standard form for an optimization problem. By the way, if you read the Russian, the Soviet literature, you'd see different things, which is actually, I guess, many Russians are now teaching in US and European universities. So it's now propagated, and you might as well know what it looks like. They would write it this way. It's actually a perfectly good notation, like that. Okay? So you will see this, and it means that f0 of x, the objective, is to be minimized. So I guess I don't know how to pronounce this in Russian, but it's something like that. But that's the meaning. So you'll see this, and you'll see some other ones. Now you'll also see some things that drive me insane, and I'll mention one of them. You'll see this. And that really, really drives me insane because the semantics is wrong. Min actually has a meaning. Like you have the min takes as argument a set of numbers. I mean, in the strict definition, min takes as argument a finite set of numbers, and it returns a number. Minimize is actually a verb. It's not a mathematical operator, and it's part of the verb that you use to create an optimization problem. So these are different things. But you'll see this. But actually, sometimes they just barely escape by putting a period at the end, which suggests that it wasn't min, it was short for minimize. But anyway, you'll see that sloppy. Okay. Now here, x is the optimization variable. This is called the cost. Or it's sometimes called the objective. It's got all sorts of other names or something. You know, if it's in a specific application area, it'll have a name too. Then these are called the inequality constraint functions, and the h's are the equality constraint functions. Now here the right-hand sides are 0. We're going to see very quickly how you would transform, if the right-hand side weren't 0, how you could transform it. So it's just useful to have a standard form like this. Okay. Now the optimal value of this problem, so the type of object or data, what this is that's an optimization problem. Sorry, without the min or with the min period. That's a problem. By the way, it has no numeric. I mean, by itself, you can't say this problem is 3 or something like that. But you can talk about the optimal value of a problem, and that's simply the infimum or minimum of f0 of x over all x that satisfy the equality constraints. And there's a completely standard convention that the infimum of an empty set is infinity. So that's absolutely standard. And that says, you'd say that the optimal value of this problem is infinity if there's no feasible x, if there's no x that satisfies these inequalities and equalities. And that makes sense, because if your objective is to minimize something, then the value plus infinity basically means you've done infinitely poorly. You could not have done more poorly if your job was to minimize something if the value is infinity. And that is, after all, what infeasibility means. It means you didn't even get to the point where you could actually compare 2 points and say yours is better than mine, because there weren't any that met the hard constraints. That's here. Okay. Now, on the other hand, this can be minus infinity. And that would be the case if there were a sequence of x's, all feasible, with f0 of xk, say, going to minus infinity. So that would be, and by the way, in different problems, this is referred to different ways. For example, in something called, in risk-sensitive estimation, they have a wonderful name for that. When the problem is unbounded below, it's called euphoric breakdown. That's the technical name for that case. So, okay. They have all sorts of other names for it in different fields and things like that. I guess it's infinitely good, I guess. Actually, what it really means is you've probably set up, your modeling of your problem is not that great, but okay. So, mention the idea of optimal and locally optimal points. Well, you say a point is feasible if it's in the domain of the objective and it satisfies the constraints. By the way, if it satisfies the constraints, it must also be in the domain of the constraint functions, right? Because you certainly wouldn't say it satisfies the constraints if it didn't also. To satisfy the constraints, fi of x actually has to return a number and not the NID token, the not in domain token. Because there's no way, if that returned not in domain, that you could actually say that the inequality was valid. Okay? So, okay. And a point is optimal if it's feasible and if its objective value is equal to the optimal value of the problem. That's optimal. And capital X opt, not totally standard notation, but I think fairly standard. That's the set of optimal points. And this can be empty. For example, if the problem is infeasible, of course it's empty. If the problem is unbounded below, this is empty. And it can be unbounded, and it can be, even when P star is finite, this can be empty. So there's this, you can have everything. In which case, by the way, to say that X opt is the empty set, the way people would say that is you'd say the optimal value is not achieved, is what you'd say. Okay? If it's finite, it means, I'll give you an example. Let's just minimize 1 over x on the positive axis. So if you minimize 1 over x, the optimal value is obviously 0. But it's not achieved because there's no x for which 1 over x, there's no x in R++ for which 1 over x is equal to 0. So you can get as close as you like and so on and so forth. So in this case, you would have x opt is empty, and you would say that's a problem with optimal value 0, which is not achieved. So, okay. Now you say a problem is locally optimal if, when you add a constraint, and notice that this depends on x. If you add a constraint that you not stray far in norm from x, r has to be positive here. So if you can add such a constraint and x becomes optimal, then it's locally optimal. Okay? And then these are kind of, I mean, you can just work through these. These are very, very straightforward. So if you minimize minus log, it's unbounded below, obviously, because I just take infinitely large x's, and a sequence of x's getting larger and larger, negative log gets smaller and smaller. Entropy, here, that negative entropy, that actually has a perfectly well-defined minimum. It occurs at 1 over e. I mean, you just differentiate, set it equal to 0. And the optimal value is minus 1 over e. So this would be 1 with none of the pathologies here. If you have f0 of x is x cubed minus 3x, here it's unbounded below. You know, obviously, as x goes to minus infinity, this thing goes to minus infinity, so it's unbounded below. But you have a local optimum at x equals 1. So if you take a look at this, you will find that around x equals 1, this thing goes like that. The derivative is 0, and in a little neighborhood around it, actually it's locally convex there, and that means that as you stray from x equals 1, the objective value goes up. So that's locally optimal. Okay, so I'm going quickly over this because it's kind of boring. So, and then when we get to the actual specific problem classes, it's more interesting. Okay. Now, when you have this standard form problem, when you write this down, there's the implicit condition. I mean, this basically says this function is what you're going to use to compare two proposed points that meet the basic requirements. The basic requirements are that you should be feasible, but there's even something even more basic. You have to be in the domain of all the f's, the objective and the constraints, and all of the, you have to be in the domain of all of the constraint and objective functions, because if you're not in the domain of them, it means that one of these things evaluates to it doesn't make sense. And you would certainly not say something is feasible if one of these things were, if you were out of the domain of one of these. So there's an implicit constraint that the only x's you'll consider are in the domain of all functions, all objective and constraint functions, the objective and all constraints. So that's sometimes called an implicit constraint because you don't write it down explicitly. Actually, merely by writing down the symbols fi and then called on x, you are actually imposing the constraint that x is in the domain of fi. Okay? So that's why it's implicit. Later we'll see there's actually a difference between implicit and explicit, and it will make a difference, but it's something to think about. When you write out the constraints explicitly like this, these are called explicit constraints. And you say a problem is unconstrained if it has no explicit constraints. And here would be a very common example, one in fact that we'll see a great deal of. It's minimize the following function. It's the sum of the negative log bi minus ai transpose x. Now, to talk about the log of something, at least if you're not in a complex variables course, but not in the context of a complex variables course, to talk about the log of something, this has to be positive. So, and in fact, our definition of log, which would differ, of course, from the definition of log used in a complex variables course, complex analysis course, our definition of log has a domain, which is r++. So merely by stating, you know, log, if I write down log of u, I don't even have to put that in the constraint. That has a side effect. And the side effect, I'm talking about a side effect the way when you call a function. That has a side effect. And the side effect is that requires u to be positive. Okay? So that's the way it will work. I mean, this is all standard, but that's the idea. So here, these have to be positive. Here. Now, to say that bi minus ai transpose x is positive says that there's actually a positive slack in the inequalities ai transpose x less than bi, like that. And this is, so the set of x that satisfies this is actually an open polyhedron. So it's an open polyhedron where this even makes sense, the domain of this. Open polyhedron. Now, on that open polyhedron, this function here is convex, it's smooth, everything. Okay? So what you would say is, if someone asks you, what about this problem? You'd say, well, that problem is unconstrained. I guess maybe if you really wanted to be specified, you'd say it's formally unconstrained. It has no constraint functions. That's what you'd say. Of course, there's an implicit, and then if someone says, oh, unconstrained, does that mean I can throw in any x I like? And the answer to that is no. You can throw in any x that satisfies this. And that's an implicit constraint inherited from the domain of f0. Okay. Let's see. Let's talk about the feasibility problem. One variation on the optimization problem is this, and it's sometimes written this way. Find x subject to. By the way, you will also sometimes see subject to written as such that, which I don't actually, that's a question of style. And by the way, this is bad style. But nevertheless, it's within, you know, it's only in the, it's between the green and it's somewhere in the yellow range for me. It's not, you know, that's not what such that means in English, by the way. Subject to are the English words that say exactly what happens when you do something subject to restrictions. You don't do something such that restrictions. That's actually not English. But you will see this. So, but not from me, you won't. So, okay. And the worst, of course, is min this. Yeah. Oh, and by the way, the initials S period, T period go either way. So it's really, you know, but I don't know. So at S period T, that's even worse, though. So, all right. So find x, subject to these constraints. Now, this just says there is no objective. And what that means is that any x that satisfies these constraints is equally attractive. I mean, there's just nothing, you're completely neutral on it just means find anything that works there. That's called a feasibility problem. And it's really the same as this, or it's convenient to make it the same as this. You make it minimize the constant objective function 0, subject to, and then these inequality constraints. Now that looks stupid, but it's not. And it encodes everything correctly. So what it means is this. The optimal value of this problem is either 0 or plus infinity. If there is a feasible point, then, I mean, any feasible point here is optimal. Because if I have a feasible point, I could ask what is its objective value, and the answer would be 0. But that's as small as the objective value gets among feasible points. If there is one, that's p star. Therefore, any feasible point is optimal here. On the other hand, if it's infeasible, then the p star is you take the infimum of 0 over the empty set, and that's plus infinity. So everything works out just fine when you do this.
Is the x opt set just the intersection of every domain and every constraint?
No, it's not the intersection of domains. The optimal set here coincides with the feasible set. So basically, in this problem, in this formulation, if you're feasible, you're optimal.
But isn't that equivalent to being in the domain of everything?
No.
How can you be in a domain and not satisfy that?
Here, I'll make an example. Ready? Let's do one. Yeah, I could say log 1 plus x is, doesn't really matter. Bigger than, I'll make it easy on myself there. Something like that. Now I have to figure out what that means, but anyway. And then I'm going to add the following constraint. Or I guess, let's see, we haven't done that. We haven't turned things around yet. So I'm going to write it like this. And then I'm going to write another one, which is minus x is less than minus 10. OK? Now, to say that you're in the domain here, there's no domain restriction from this one. There is a domain restriction here, and it's that 1 plus x should be positive. Okay? But that's not the same as the feasible set. The feasible set, this says that x should be bigger than or equal to 10. That's the feasible set. Okay? So that they're different. They're not the same. You have to go back and look at it carefully. Okay. Now, I can say what a convex optimization problem is a mere 3 weeks into the class. Actually, I kind of said earlier, but anyway. Okay, so here it is. There's a restriction, and the restriction is this. The objective must be convex function, and the constraint, the inequality constraints must also be convex. Okay? The equality constraints, that is the HIs, must be affine. And that means I'll write them this way. I can also just write it as AX equals B in very compact notation. Okay? Now, if the objective is quasi-convex, then this is called a quasi-convex optimization problem. And you might just write it out this way. This is where I've just substituted for the equality constraints a single matrix vector equality constraint. Now, the feasible set of a convex optimization problem is convex. But watch out, because there's another definition of convex optimization problem. So I guess it's what I call, there's the strict definition, and there is the looser definition. The looser definition actually makes more sense, is more appealing, and so on. And it's actually, in terms of actually doing convex optimization, it's useless. But let me say what it is. And it sounds right. If someone just bumps into you on the street and says, what's a convex problem? You would say this. It's minimizing a convex function over a convex set. What could be more natural? Okay? And that is, and in fact, that's called the abstract or the loose definition or something like that. And in fact, it's okay. But I want to point out here that for us, an attribute, so to say it's a convex optimization problem, it is not an attribute of the feasible set. It's an attribute of the problem description, period. Okay, so there's other weird ways to write AX equals B, and they will not work with these things. For example, I could write this. I could write AX minus B norm equals 0. You have to admit, if norm AX minus B is 0, AX is equal to B. So I haven't changed anything here. That's not a convex problem in the way we'll describe it, even though it's absolutely equivalent to one with AX equals B. Okay, so for us, whether or not you're a convex optimization problem is an attribute of the description of the problem, and not, for example, the feasible set or something like that. And this will be clear in a couple of cases. Here's a simple example. Let's scan this problem for convexity and see what happens. Well, the objective, what do you think of the objective? Well, the objective is okay because it's convex and you're to minimize it. So the objective is cool. And let's pass on to the first constraint. Well, we're already in trouble with the first constraint because this constraint here defines a convex set. The first constraint, it's nothing but x1 is less than or equal to 0. Obviously, right? 1 plus x2 squared is positive. I can get rid of it. So, however, this is f1. As I've described this problem, that's f1, and that is not a convex function. And so this problem is rejected, is not convex. Okay? And the second one also is not convex because that is indeed a convex function of x1 and x2, but you're not allowed to have a convex function equals 0. You can have convex function less than or equal to 0. So this, I would have to call that f2 now. This actually would have been okay. That would have been fine. That'd be a convex problem because you have a convex function here less than or equal to 0. But the point is here is you take these and you rewrite it in an equivalent way. By the way, these are not identical problems. The problems are identical only if the objective functions and constraint functions are identical. Then the two problems are identical. However, they're equivalent. And we'll use a kind of an informal idea, but nevertheless completely clear idea of what equivalent means. Equivalent means that by solving one, you can construct the solution of the other, and vice versa. And construct it means with not using too much work. Okay? So it's something like, I mean, if you've had a course on complexity theory and computer science or something, it's something like that, except that we're not going to be very formal about it. It's something like, a polynomial reduction of one problem to another. Okay? So that's what we mean by equivalent. Except that we won't get too fancy about what types of equivalences are there. For us, it's going to be an informal idea. So, yeah.
When you say they share a solution set, do you mean both in terms of the value of x and in the optimal value of x?
Absolutely. In this case, well, I didn't change the objective, so that's why I could change the objective, right? So for us, equivalent problem means this: that I think the best way to say is that you could write a very thin wrapper code around one problem that would then solve the other problem. That's what it means. Okay? And in this case, it would be very thin. I mean, what would happen is this. To solve this problem, you would solve that one and then return the solution. So that's pretty thin wrapper that goes around this. So that's what it means. In other cases, we'll see you might do other things. Oh, actually, we're going to see lots of little equivalences, and I'll make it very clear what's happening. But that's the right way to think of equivalence as we'll use it. It means writing a wrapper around one to solve the other. That's what it's going to mean. And a wrapper, by the way, that doesn't do like a huge amount of work. Okay. So let's say a little bit about local and global optima. So if you have a locally optimal point of a convex problem, it's globally optimal. This is, by the way, the kind of thing that people on the street would know. This is kind of the basic thing you'd know about convex optimization, would be this. And I don't, variations on it. And it's actually very impressive if you think carefully about it, right? It basically says if you have a problem, if you have an optimization problem, it says if you were to restrict your search, you have a point, which is a candidate for being optimal. And it says if you restrict your search arbitrarily closely, locally, but if you do a full search in there and find that there's actually no better point locally, you can make the stunning conclusion from having examined this R ball, which is tiny. In fact, it can be as small as you like. You can make the stunning conclusion that, in fact, even if you were to search over everywhere, there'd be nothing better. So, although, after a while you get used to it, the proof of these things is like 3 lines or something like that. So it's not like, it's not a big deal. Still, what it's saying is actually stunning. I mean, if you think carefully about it, right? To say that well, it's actually highly implausible if you think about it. It basically says, look, if you do a competent search nearby and find nothing better, then in fact, you don't need to go and look anywhere else. This is the best you can do. Of course, that's inherited from all the properties of convex functions and so on. But okay, so let's see how you would show this. It's actually totally straightforward. Suppose you have a point that's locally optimal, but not globally optimal. And what that means is there's a point another point that's optimal. In fact, you don't even need the point to be optimal. So you just need a point with the feasible and has objective value better than your locally optimal point. So suppose that happens, then it's very simple what to do. You simply construct the line segment between your local optimum and this better but feasible point. You construct the line segment and you start moving towards from where you are locally optimal to this point that's better. What happens is that, of course, as you move on that line, you remain feasible because x is feasible, y is feasible, the feasible set is convex. Therefore, all along that line segment, you will be feasible. Then what can you say? Well, now you have a convex function that basically is locally optimal at first, but then later actually achieves a value lower. And of course, that's impossible. So that's the idea. It's very, very simple to show this. And I won't go through all of these details, but that's kind of the idea. That's what I just described is it. Okay. Let's look at an optimality criterion. Again, it looks very simple. It's very geometric. And it's going to generalize what you've seen before, this idea of the gradient vanishing being the condition for optimality. So here it is. A point x is optimal. This is for a convex optimization problem. If and only if it's feasible. And the following is true. It says that the gradient of the objective evaluated at the point x transpose times y minus x is bigger than or equal to 0 for all feasible y. Okay? Now, geometrically, it means this. Here's your feasible set. Here. These are the level curves of the objective. And so this is clearly the optimal point. It's the point in the feasible set with the lowest objective value. So that's right here. You write the gradient of the, actually you write the negative gradient. You write the negative gradient of the objective function. That would be the normal to the hyperplane here, the local hyperplane of approximately constant objective, like this. And it says that this hyperplane here actually supports the feasible set at that point. It looks like that. That's the picture. Okay? And it makes, I can actually sort of explain this. Let's go. It just comes from this thing, right? It basically says the following. You know the following is true, right? F of x plus, if f is convex, this is true for all y. Okay? So if these are the level curves of your function, like that, and I evaluate it, say, here, and the negative gradient, points in that direction, it says basically if I draw this hyperplane like this, this inequality tells me something. It says that every point in this entire half space here has a function value higher than the function value there. That's what it says. Okay? In particular. Because if this is non-negative, then that's bigger than that. So that's the basic inequality comes from that, or the basic geometric conclusion is that when you evaluate the gradient of a convex function, and it says points in like this direction, it says that all the hyperplanes, I guess, well, the hyperplane, the half space that's aligned with that normal, all those points have worse value of f, and there's no point even looking there because it's absolutely guaranteed. So what this says is all feasible points live within this half space here where the objective is worse than or equal to the value there. Well, guess what? That means that point is globally optimal. Okay? So, and by the way, to show the if and only if, it's very easy. I just showed one way. The other way is even easier. If this is true, then this basic inequality proves it for us. So it's quite straightforward. So this is it. So by the way, this innocent little condition here. Oh, and notice that if the problem is unconstrained, let's see what this says. Well, we'll look at these in list fashion. So let's take this simple. By the way, we're going to come back and we're going to look at optimality criteria in much more detail later. Much more detail. But for now, this is just your first glimpse at optimality criteria for convex problems.
What happens if the objective is not differentiable at that point?
Then this doesn't apply. Okay. Yeah. So the question is, what happens if the objective is not differentiable at that point? And my response was, then this doesn't apply. Okay. So let's look at an unconstrained problem. Well, let's see, what would it mean to say, if it's unconstrained, then this is just basically for all y in Rn. So, hey, wait a minute. If I can choose y to be anything I like in Rn, this vector here can be anything I like. What does it mean to say that I have a vector g, let's call that g. Suppose I told you that g transpose z is bigger than or equal to 0 for all z in Rn. What's your conclusion? Yeah, g is 0. Yeah. But how do you know that, by the way? What's a quick argument for that?
Because if g is not 0, you can always choose z to have either
Yeah.
positive or negative.
Okay. Yeah, sure. Okay. Yeah, here's a, you want a quick snappy one? Try that. Yeah. Try that z, and you'll get your conclusion real fast. Because you get minus norm g squared is bigger than or equal to 0. So, yeah, so g has to be 0. That's the only way. So, so this condition, which looks kind of complicated. I mean, it's not actually. The only thing you have to remember is this picture. So you remember this picture, then there's nothing more to say. So here, the condition is that the gradient is 0. Equality constrained. That we can also get this, and this will recover these things like Lagrange multipliers, which you've probably seen earlier. You will see again. So you want to minimize f0 of x subject to ax equals b. Well, x is optimal if and only if, I mean, the condition is this. You're feasible, and the gradient plus A transpose nu is 0. Now, to show that, and I'll just give a quick plausibility argument, not give the whole argument for that, but I'll show that. It says basically the following. The gradient of f0 of x transpose z minus x has to be positive for all z that satisfy a z equals b. Okay? Something like that. Well, there's many ways I can write this. Actually, it's even more interesting. We also know that ax equals b. And what we see is that it means that z minus x is in the null space of A. Okay? That's what this says. So this says that the gradient of f0 of x is orthogonal to everything in the null space of A. So we're going to write that this way, like so. Okay? Oh, you know what? Sorry, I skipped a step. Sorry. The gradient has non-negative inner product with everything in the null space of A. However, if you have a subspace, if you have a non-negative inner product with something in a subspace, then it also is non-negative when if you reverse the sign of z minus x, which is still in the subspace, it's still in the subspace. Therefore, you have a non-negative inner product with a vector, and you have a non-negative inner product with its negative. That means you have to be 0. I forgot. I skipped that. So that says this: grad f0 of x is in the null space of A perp, or something like that. It means it's orthogonal to the null space of A. Okay? Now that is the range of A transpose. So that says grad f of x is in the range of A transpose. That means that grad f0 of x is equal to A transpose times some u. And I'll later make you, I'll mess with you to make it fit our form. Okay? But actually, I'm kind of done, because I could write this as grad f of x, and let's see how I wrote it here. Yeah, plus, I can write plus A transpose times minus u equals 0 for some u. And I should have, I guess if I were smart, I would have put the minus, but it would have been kind of weird. But anyway, so there we go. That's the condition. So, and by the way, don't worry about these. This is just your first glimpse at this. We will spend week and a half on all these things later in much greater detail. Okay, now it starts getting interesting. It could be argued, I mean, I presume that you would know this or have heard of it. I would presume you heard this. Generally, Lagrange multipliers are taught as a behavior in an advanced calculus class somewhere, where someone says, how do you solve that? And the answer, you're taught the following. Then you should do this. And I don't know, doesn't make much sense, but you're told that's what has to happen. this would maybe be the first one where it's not obvious. It's something maybe you haven't seen. So what are the conditions under which, when would a point x in the non-negative orthant minimize a convex function? That's the question. Well, let's just apply we'll end up deriving it. But it's going to look something like this. It basically says grad f of x transpose times z minus x has to be bigger than or equal to 0 for all z positive. Okay, that's our basic condition. And let's simplify this now. So let's take a good look at this. This has to be positive for any non-negative z here. So let's see what happens. Well, first of all, I can plug in a bunch of things. I can plug in z equals 0, and I get the following. The grad f of x transpose times x is less than 0. Everybody agree with that? That's from z equals 0. And now I can do the following. I could let z, if an entry of this vector were negative, I'm in big trouble. Because if an entry were negative, I would take z, if the ith entry of this thing is negative, I take z equals t times ei. And then I let t get super big. Then what happens here is this thing here, as t goes to infinity, this thing is an affine function of t with a negative slope. And there's no way it's going to be bigger than or equal to 0. So we can also conclude that this vector is positive. There's some squiggles there. These are straight, no squiggle. These are squiggled. Okay? But now it's getting interesting. Because look at this. I have the inner product of two non-negative vectors. And it's less than or equal to 0. Now, when you take the inner product, you take the sum of the associated products. But obviously, if you're doing that with two vectors that are non-negative, and you end up with something that's less than or equal to 0, there's only one choice. It has to be 0, number 1. And number 2, it has to be complementary. In other words, we actually can say this. So basically, it says, if xi is positive, then that component of the gradient is 0. And vice versa. If this is positive, that's 0, period. This is called complementarity. And you're going to see it a lot, or you'll see it a bit. Okay? So that's the condition here. We just worked out this. So, and these are, it's already, these are kind of not these are not totally obvious. Okay. Next topic is equivalent convex problems. So, as I said, we're going to use an informal notion of this. You say that they're equivalent if the solution of one is obtained, with modest effort from the solution of another. And what we'll do is just give a bunch of common transformations that would preserve equivalence. Just examples to give you a rough idea. Here's one. You could eliminate equality constraints. So I want to minimize f0 of x subject to fi of x less than 0 and ax equals b. I could eliminate these. And the way I do that is I find a matrix F and a point Z so that ax equals b is equivalent to being having the form fz plus x0 for some z. Now, how do you get f? I mean, these are quite easy. F is like the null space. The columns of A would be a basis for the null space. Not a basis, sorry. They would span. That's all we have to do. They would span the null space of A. And then x0 is any particular solution of ax equals b. I mean, for example, it could be the least norm solution, for example. So it's just linear algebra to go from AB to f and x0. So, but the point is, this is what people would call a constrained representation of an affine set. And this is what people would call a free parameter representation. So this is parameterized by z, which is now free. Okay? If it's a minimal one, you could say something about the size of these things, but that's just linear algebra. So what I'll do now is I'll make a new problem, which is this. I'll just take x equals fz plus x0, and I get this problem here. I don't need this constraint because basically a fz plus x0 is equal to b for all z automatically because af is 0. That's how you constructed f. And ax0 is b. That's how you constructed x0. So you don't need this constraint. You drop the constraint, and you get this. Now, these are not the same problem. I mean, they're totally different. They have different dimension variables. This one has equality constraints. This has none. But they're clearly equivalent, and the idea would go something like this. If you wanted to solve this problem, you would, you'd solve this problem and then return as x fz plus x0. That's what you'd do. Okay? Now, the idea that it has to be a modest transformation to do this has something to do with the following fact, that when you get a and b, it has to require modest computation to calculate f and x0. And indeed it does. That's just basic numerical linear algebra. Yeah.
Construct f again?
Oh, the columns of f are, for example, a basis for the null space of A. That's good enough, right? So you get it there's many ways to construct such an f like that. Okay, so this is and by the way, if this problem is convex, so is this one. And the reason is that the objective is actually you precompose with an affine function. But if you precompose with an affine function, that preserves convexity. Okay? This one is unconstrained. No equality constraints. Now you can do the opposite. And in fact, the shock, or hopefully within 3-4 weeks, you will, later in the class, there'll be like, I don't know, when you, somewhere near the 9th week of class, you'll think, what were some of the shocking things that, a lot of it kind of sort of made sense intuitively, but some of it will be, there'll be things that where you'd actually say, okay, well, that wasn't obvious. Okay, now I'm going to tell you one. I mean, this is just the topic, but we'll get to it. It's this. It's actually often extremely useful to introduce equality constraints. So to uneliminate. And there you have everyone has a bias towards elimination because people like to solve problems with smaller numbers of variables. I will cure you of that before this quarter is over. So if you know what you're doing, not only is it sometimes not a good idea to eliminate constraints, it's often a good idea to introduce new variables and constraints. Which sounds very odd when you first see it, but trust me, before the quarter is over, it will be very natural to you. So, yeah?
Yeah, why do the equality constraints have to be affine if we're just going to compose them and need to preserve convexity? Couldn't we just have any convex?
Well, my answer to that, which is, the question was why do the equality constraints have to be affine? And so my question is going to be very my answer is going to be very unsatisfying to you. It's this. That's our definition of a convex problem. So by definition, a convex problem, the only equality constraints we have are affine. Sorry. Well, generally speaking, other affine constraints don't lead, then the constraint set generally is not convex. And then you don't even meet the broader definition of a convex problem, which is minimizing a convex function over a convex set. So, sorry. So it's by fiat. Convex problem has affine constraints. So, I told you wouldn't like the answer.
Yeah.
Yeah. Oh well. Sometimes there's good answers. Sometimes there's unsatisfying ones. That was the latter. Okay. Okay. So how do you add? I mean, you can actually introduce equality constraints, which, by the way, some people call unelimination. I kind of like that. So it works like this. You have a problem that looks like this. You could do the following. I'll introduce a new variable, y0 here. I'll introduce a new variable, yi here. And I'll have this problem. Minimize over x and now also yi. So I've added new variables. f0 of y0 subject to fi of yi less than or equal to 0. And then these equality constraints. Now, you could reasonably ask, it's entirely reasonable to ask a question, why on earth would you add extra ridiculous variables? Because, I mean, this doesn't look like progress, okay? I mean, the problem started with no equality constraints. After this unelimination step, you have added variables and added equality constraints. This does not look like progress. Later you'll see, shockingly, this is the first step to lots of progress. I know it's weird, but this will all be clear later. So, all right. Another trick is to introduce slack variables for linear inequalities. Now, that works like this. You're going to say, well, I have AI transpose x is less than bi. That's fine. What I'll do is I'll convert that to an equality constraint. I'll convert that to AI transpose x plus SI equals BI. I mean, that's stupid. This is the same as saying SI is the slack. It's BI minus AI transpose x. And then I'll write that the slacks are bigger than or equal to 0. Or to put it in our absolutely canonical form, I would write minus SI is less than 0. Okay, here, to put it this way. So again, these are simple. Actually, what's remarkable is that we're going to look at a bunch of transformations. Most of them are like really stupid, like these. And it's weird to think. Yeah, it's like everything else. You learn about 15 trivial things, and then you put them together in just the right sequence, and all of a sudden something that was not obvious at all will come out. So, yeah.
When you minimize that problem, don't you know for a fact that the minimal SI will be 0, or S will be 0, since, you want to push up against the valve?
No. Also, that's not true. That's just not true.
The slack may actually
be
finite.
The slack can be positive, sure. It depends. It's basically you solve that problem. I mean, so if you want to, by the way, each of these needs an argument that there actually are equivalent. And it's, so don't just trust me. After you do a few of these yourselves work these out, you'll see. Also, you'll probably do some of these numerically and basically, and if you don't know what you're doing, you'll just come out with the wrong answer. So that'll be another feedback mechanism for you. But let's just check here that they're equivalent. Well, if I solved this problem, then I can define SI equals BI minus AI transpose X. Now, if you solve this problem, it's feasible, so the SIs are positive. And those SIs are feasible for this, and in fact, they're optimal. But I'd have to argue that, which I'm not going to do. Then you can go backwards, and you can say, well, suppose someone solved this. We're going to make a bidirect, the wrapper, that would allow you to solve this problem if you had code that solved this, or if you had the solution for this, or whatever. So if I solve this problem, I just drop x, and I return. The solution of this one gives me x and s. And I simply drop x and forward x, and argue that it's actually here, it's optimal here. So that would be the argument. I'm actually not going to do it, because these are actually shockingly boring, but should be done once, or twice, or something, or more. But not many more times than that. And you will, I promise.
Wait, so what does it mean to minimize over x and s? Is there another objective, or?
Nope. No, it just means I have more variables. So it means that when you minimize over x here, it just means x is what you can mess with. Here, when you minimize over x and s, it says you have x and s to mess with. So that's what it means. Here's a simple trick. It's called the epigraph trick. It's actually quite useful, and it's widely used in practice. Let's see how that works. It's really dumb. Here's what it is. You want to minimize f0. You introduce a new scalar variable t, and you introduce this new constraint, which is f0 of this is basically f0 of x is less than t, and you minimize t. Now, this is kind of dumb, because if you solve this problem, first of all, you'd be an idiot to choose a t, any t other than f0 of x equals t. Not an idiot. It'd just be that t couldn't possibly be optimal, is the point, okay? Because your goal is to minimize t. So, however, I cannot adjoin this to this problem. It is an equivalent problem to write equals here. That's absolutely equivalent to the original problem. Unfortunately, it's not convex unless f0 is affine. Okay? However, with the less than or equal to, it's convex. And it's a really dumb thing. Let me just draw this. Here's a function that you want to minimize, like this. The original problem basically says, find the point here that minimizes f0. This one, it does this ridiculous thing. It introduces a new t that's up here, like that. And it says, that's your feasible set, or something like that. And then it says, go as far as you can in the direction negative t, right? Like that. Actually, I guess the direction is -1. And you would recover this point here. Okay? By the way, this has immediate practical applications. This says, for example, that if you're going to write a code to solve convex problems, you don't need to without any loss of generality, you can just minimize a linear objective. Okay? And that's quite standard. So you look on if you go to Google and type, C source and then some name of some convex problem, you will find it'll just, many times they won't even say it. It'll just say it solves the following problem and it's a linear objective, and you go, hey, I can't use this. My objective is not linear. Well, it's just expected that you know this. So this is just expected. By the way, it's generally not in the documentation, which is actually interesting because that's how widely this is supposed to be known. It's also how unhelpful the documentation is. So this is the epigraph trick, and you'll see this used quite frequently. Oh, the other thing you'll hear is this. Oh, you'll actually have people say, just without loss of generality, the objective can be assumed to be linear, because that's a linear objective. That's a linear function of x and t. So that's just completely standard. You'll also hear people say things like this. They would say, linear objective is universal in convex optimization. So whatever that means, it means something like, if you can do linear objective, you can do anything. So, okay. A couple of other equivalences. Here's one. You can minimize over some variables. So if you have a problem that says minimize f0 of x1 comma x2 subject to fi of x1 is less than 0, for example, I could minimize this thing over x2. And that would give you this function f0 tilde of x1. And that would give me this. So, by the way, for those of you who have seen dynamic programming, for example, that would just be this, a fancy version of this would just give you all of dynamic programming. And basically then there's nothing to say about it, except it's just this. Except, interesting point. Dynamic programming preserves convexity of a problem. So you have a problem of two variables, or in the general case, a whole bunch of variables, for example, stages in an optimal control problem or something like that. If you minimize over some of the variables, you have to take account of that in the constraints, the objective, everything. But when you minimize over one family of variables in any convex function, the result is a convex function. So we can now say something like this. Dynamic programming, if you know what I'm talking about, preserves convexity. So when you optimize over the last stage variable and end up with if the original problem were convex, over capital T stages, the T minus 1 stage problem also convex, and the T minus 2 and so on. Okay. Just out of curious, actually, how many people have heard about dynamic programming and stuff like that? So, okay, so not empty, not an empty set. Okay. Quasi-convex optimization. Well, here, F0 is quasi-convex. There are lots of actually practical problems that are going to be, we'll see lots that are quasi-convex or something like that. And here, you have to be very careful because, for example, this most basic thing, which says a locally optimal point is globally optimal, is completely false. And here's a perfect example. I'm making it exactly flat here. Okay? So that's a locally optimal point, no doubt about it. And it is obviously not the global optimum here. So, and that's a perfectly valid quasi-convex function. So, so a lot of things are different now and need not be right. But here's how you solve them with total effectiveness. Works like this. Generally speaking, if you have a quasi-convex function, unless you're just doing a theoretical analysis, if you're actually going to do anything, that is to say construct an algorithm that solves a problem, solve an actual problem, or anything like that, other than just talk about it, then what's going to happen is this. You're going to actually want a convex representation of the T sublevel set. So it's not enough to say, so you construct a convex. Now, convex representation looks like this. It says that you look at the sublevel set, and you must write it as, I've written it as one convex inequality, parameterized by T. But you don't have to. It can actually mushroom to a bunch of convex inequalities. It doesn't matter. You need a convex representation of the sublevel set is what you need here. Here's an example. It's a general fact that if you have a ratio of a convex to a positive concave, actually non-negative convex to a positive over a positive concave function, this function here is actually quasi-convex. Okay? It's very easy to show that because, well, there's some horrible details. But let's do this. You want to know, is that a convex function of x? By the way, if this were a convex function of x and t, that would be the proof that this function is actually convex in x. It's not convex, it's quasi-convex. That means t, consider fixed, and you want to know is the set of x that satisfies this convex. That's the question. Okay? So if you look at this, well, you just multiply through, and you get p of x is less than t times q of x. Now you're in pretty good shape, because I write that as p of x minus t q of x is less than 0. That's convex. That's concave. Okay? T is bigger than or equal to 0 without loss of generality, because if t is negative, the sublevel set is empty and convex. So I've already dealt with that case. Then this is convex minus non-negative multiple of concave. This whole thing is convex. That's a convex representation. Okay? Depends on t affinely, but that doesn't matter. In fact, the dependence on t is completely irrelevant. Okay? Now the way you solve a quasi-convex problem is this. You just solve it. If you think about what you can do now, if you have this convex representation for any t, it means you can do the following. You can actually ask a question like this. You could say, is the optimal value less than or equal to t? And you have to solve a convex feasibility problem to determine it. So you could say, look, is the optimal value less than 3? And the answer could be no. Okay? Then you start with a value of t where the answer is yes, like t equals 10. Then of course you'd do bisection. So you'd take the average of these, you take 13, and then the next query would be 6.5, and so on and so forth. So that would be basic bisection, and that looks like this. So you start with a lower and an upper bound on p star. By the way, you might not have that, in which case sort of a practical version of this would start with t equals 1 and query. And if that is infeasible, if it's infeasible, you would then try t equals 2, then 4, then 8, then 16, or something like that. And then when you get to a big enough number that you wouldn't be interested, even if it were feasible, you would quit. So that would be one way. If it's feasible and you don't have a lower bound, you'd start with t equals 1, then you try a half. If that's feasible, you try half, quarter, and when you get down to something very, very small, you'd quit. Okay. Well, sorry, that's all the assumption that it's a positive function that you're minimizing. So, okay. So you start with a known upper and lower bound on p star, and you simply query at the midpoint of your known upper and lower bounds, and you solve the convex feasibility problem. And this is just bisection. And every time you do this, your interval, you end up with 2 points, an L and a U. L is you actually have an X. Where sorry, you don't have an x. For u, you have an x that actually has at least has at most the value f0. F0 of x is less than or equal to u. And L, on the other hand, is a value known to be infeasible. There's no x that satisfies f0 of x is less than L. So anyway, and then at each step, that interval of ignorance divides by 2. So your ignorance halves at each iteration. And so it takes 10 steps, and you reduce your ignorance by 1,000, and 20 steps, 1,000,000. Roughly. That's the idea. Okay. So, and yes, you'll definitely do this at some point.
Convex feasibility probably wrote up there has objective 0 implicitly.
Right.
Okay. And what does the colon equal mean?
Where?
In the bisection method? Yep.
That's an assignment.
Okay.
Yeah. Okay. All right, now we're going to start in on, we're going to look at some, we're actually going to look at some, at problem families. This is actually quite interesting, quite useful. All of this, the problem families are interesting mostly because you can actually, all the things we're going to look at actually are extremely practical. I mean, so what we've done so far is all very general and would follow a traditional course on this material, right? And then it would stay at that level. We start talking about the things we're going to talk about now are extremely interesting theoretically. In fact, some of them are at the height of fashion in various fields at the moment. Not linear programming, but other things we'll see are at the absolute height of fashion. Even among people doing strictly theory. And it's very, very interesting. But actually what's mostly interesting about it is that all of these things are extremely doable. So you can do these. In fact, you will shortly. So, so that's sort of we're now moving into things that's more than stuff you talk about. These are things you can actually do. So, thought I'd point that out. So, linear program. A linear program it's almost sort of the simplest optimization problem there is in one sense. All of the functions involved are affine. Everything is affine. The objective is affine. The inequality constraints are affine. By the way, people call them linear. So that's okay. And the constraints are affine, again called linear constraints. It depends on whether when you say affine or not, linear, you allow an arbitrary right-hand side. If you allow an arbitrary right-hand side, then of course when someone says linear, it means affine. Okay. So that's an LP. By the way, this is not a new topic. I mean, just to make that clear, not remotely a new topic. So Fourier wrote a paper about this, which is a hint that this is not exactly a new topic. In fact, he wrote a paper on how to solve linear programs. It was a method that would be very effective if there were like 4 variables. But hey, that was the beginning of the 19th century. Anyway, so modern history actually has a lot to do with Stanford. And for that, but to be fully honest, it has a lot to do with Moscow State University. And later Stanford, but it has a lot to do with Stanford. So, because this was sort of popularized in around 1948 by a bunch of people who were here, like George Danzig. Okay, so the feasible set, of course, is a polyhedron. So your image of what an LP is should be this: there's a polyhedron, and then the objective is affine. So I mean, the level sets of an affine function are hyperplanes. So you're just, here's negative c, and you're told go as far as you can in this direction. And this little example makes it totally clear. That's the solution. Okay? So now, before you imagine that this picture, though, really fully does the trick of understanding it, I should point a few things out. If you have a linear program with like, 30 variables and like 100 inequalities, okay? The feasible set, it's a polyhedron. It's a polyhedron. You want to know how many vertices it has? Someone want to take a guess? I forgot what numbers I said. But so if what I'm about to say is a lie, it would become true by increasing those numbers modestly. The answer is just completely astronomical. It's just absolutely astronomical. Goes up very quickly. So you can write down a very small, what's called a small linear program, and the number of vertices it will have on this polyhedron will simply be literally astronomical. It doesn't take much. You will solve in this class many linear programs where the number of vertices in the feasible set will exceed, probably by a long shot, the number of subatomic particles in the universe. Okay? So you will solve many of them. Quickly, I might add. Okay? So I just point this out because this is the picture you should have. This is what I think of when I think of an LP. But be forewarned that this doesn't really give you a full. When you look at this, I mean, like if you were to go, if your roommate asked, what are you doing? You said, yeah, it's really we learned today how to go as far as you can in this direction on this set. They'd look at that and they go, when's the drop deadline? Is what they would anyway. So just watch out. The pictures explain it, but I don't think you get the full idea of it. So all right, so let's look at some examples. Here's a famous one. This is just here for historical purposes. So it's the diet problem. So you're supposed to choose a bunch of foods. So you have n possible food types, and you're going to choose some quantities that you're going to feed some group of people. I don't know, presumably soldiers. I don't think anyone would eat this willingly. Well, what's going to happen here? But so you're going to feed some people some amounts of food. 1 unit of food costs, you have these costs, which are Cj. And each one contains Aij of some nutrient. That's like, whatever, 10 grams of the food or whatever a unit is here. And a healthy diet requires, at least BI units of some nutrient. So, all right. So how do you find the cheapest healthy diet? Well, you minimize C transpose X. Now, C transpose X here is literally the cost, because Xi is the quantity of each one of each type of food you're going to put into this mixture, And then when you take the inner product with C, that gives you the actual cost. Okay? So that's minimizing the cost. Subject to AX bigger than B. A is nothing but this matrix here. It's the nutrient matrix or whatever. And then B is this minimum daily allow, whatever, something like that. Okay? So this is, it's a famous problem. X has to be positive. You can't feed people negative amounts or whatever. So that's the now, whether you'd want to eat this diet is another story. And of course, I mean, it doesn't take much here to realize it's a fairly poor model. It assumes these things sort of add linearly, which might not be the case. You might impose, could I impose an upper bound on the amount of a nutrient or something like that here? And of course I could, and it would still be a linear program and so on. But this is just for historical reasons. It's sort of the first one you would hear about. Okay, here's one. Piecewise linear minimization. So you want to minimize the maximum of a bunch of affine functions. So you just want to minimize that over x. Okay? Now that's an interesting problem because it's not remotely linear. Not even close. In fact, when it's linear, it's boring because I know how to minimize a single affine function. The answer is minus infinity. So this is not linear, not remotely. There's nothing linear about that problem. It's also quite useful because actually piecewise linear functions can be used to approximate actually any convex function. So although this looks kind of silly, it's way more powerful than you think. Okay? So just minimize some piecewise linear function. It's an LP. You just put it in epigraph form. So you just write it this way. I'm going to minimize a new variable t subject to AI transpose x plus bi is less than t. Done. Now it's linear. Now the variables are x and t. These are affine linear inequalities, or to use the term that most people would use, linear inequalities. These are linear inequalities in x and t. That's it. Okay. By the way, this is the reason you need to know this. There's some reasons you need to know it. Because if you went to Google and typed source code PWL minimization, you would find actually what you'd find is terrible stuff from total backwater fields where they don't even know it's a linear program. That's what you'd find. And it'd be the worst stuff you've ever, if you found anything. Okay? So on the other hand, you won't find anywhere anything that would tell you if you didn't know that piecewise linear. So I think that's the problem. Everyone knows piecewise linear minimization is equivalent to an LP. So what you really want to do is get LP solvers, of which there's tons. So, in fact, sadly, if you went to Google and typed that, you'd probably go to this PDF file. But the others would be very bad, I assure you. So, okay, we'll look at another one, and it's the Chebyshev center of a polyhedron. Now, we already talked about this a little bit. We talked a little bit about the idea of yield maximization. So, yield maximization was this problem. And this is just to sort of set this up so you'd know why you would want to do, for example, Chebyshev centering or something like that. Yield maximization was that we had some polyhedron of acceptable values of some parameters. We're going to set a target for manufacturing. So we're going to set our machines to attempt to manufacture these points. In manufacture, however, you will add a random perturbation to this point. And so what you'll get is you'll get a PDF that is centered, has mean value at this point, but otherwise, tails off. And then we're interested in maximizing the probability that you're in this set. That would be the yield. Okay? That's actually generally a hard problem, although convex if the PDF is log concave. But there's actually a simpler method, is to simply say, look, what you really want is you want that point to be well centered. You want it deep in this set. For example, if the PDF were N0I, so it was if the perturbations were Gaussian, uncorrelated, then basically it says that if you looked at the PDF, the level sets would be circles. And so basically what you might argue then is you want this thing to find the point here where the largest circle around it fits in the set. It's a heuristic, but it's something would actually work very well. Okay, just something like that for a nice rounded perturbation. So that leads you to this idea of the Chebyshev center of a polyhedron. And what is that? Well, I'd have a, a bunch of inequalities, my polyhedron. And what I want to do is I want to find the center of the largest ball that fits inside. So another way to say it is that's the point that is deepest inside the set. I can define the depth of a point in a set as the minimum distance to the complement of the set. It's basically how far you are from the outside. Okay? That's the depth of a point. Okay? And what I would want to do is I want to find the maximum depth point. I want to find the point deepest in this set. Now, by the way, you're drawing pictures with spheres and balls. The whole thing says find me a Euclidean ball. But that means that if that's not going to trigger the linear portion of your brain. It shouldn't anyway, right? So if you talk about linear things, flat is what you should, the portions that light up when you think about flat things should be flashing. But when I start talking about things like ellipsoids and balls and round things, that should just suppress all of the brain activity in the lobe that handles affine things. Turns out that's wrong. So watch this. So I'm just saying that when someone tells you, please find the center of the, when you see like ball, you should think round. Round should suppress the linear, and you would not at that point imagine this is going to turn into an LP. Well, it is, and the reason it's quite straightforward is this: AI transpose x is less than bi for all x in this ball centered at xc. That's easy to do. I simply maximize this thing over the ball and see whether that is less than bi. But this is nothing. It's AI transpose xc, that's the center, plus the sup of AI transpose u when u is constrained to be less than r, and it's equal to this. Okay? Now, so the inequality that you should stay on one side of a half space is in fact here. And shockingly, it's linear in xc and r. And so you can do Chebyshev centering this way. You maximize r subject to AI transpose xc plus r norm AI2 less than bi. Now watch out, because the norm should also be triggering your nonlinearity detectors. Okay? However, the norm is applied to data, and it has no effect. The variables here are xc and r, and these are linear inequalities in xc and r. Question?
I don't see why this thing has to be unique, especially with like a regular polygon.
What has to be unique?
The Chebyshev center.
Right. It doesn't have to be.
Okay.
Right. You're right. It does not have to be unique. So it's a very good point. However, what this does is if it's not unique, this LP will construct an optimal solution. And by the way, I should mention, essentially that's the semantics of an optimization problem. So if I put an optimization problem down on the table in front of you, all that can be asked of you is to produce a solution. So if someone then comes back later and says, hey, wait a minute, I got two different solutions, that's not cool. It's only not cool if one of them is either infeasible or if one has an objective better than the other, in which case you have to get rid of the person who produced who alleged that their non-optimal point was optimal. But in general, now, by the way, if it really matters to you that it should be unique, then there's actually ways where you can add a secondary objective or something like that to this. But that's a very good point. And in fact, for Chebyshev center, it doesn't have to be. Just take a rectangle, and it's completely clear. Take a rectangle, you can fit a ball in it, but that ball can move. But any of those points technically solves the Chebyshev centering problem. Now, for yield maximization, you would further want that ball to be in the center, right? So, but just to give you, but that's a very good point. Yes?
Does this apply only to the L2 norm? The fact it's an LP?
No, you could, this would be easily generalizable to other norms. Okay, very simple. All that happens here is, if that's a norm, that's the dual norm. Okay? So, no, here, I'll just do it right now. There. There, done. Now it's general norm. Okay? And now you can't call it the Chebyshev, it's the general norm maximum depth point ball in polyhedron problem. Or something like that, anyway. So you can probably get some good acronyms out of that. But but we won't do it because we're out of time. Actually, the only thing I will say about this is it's, you know, this is a really simple example, but it's actually very cool. Let me tell you why it's cool. Because, you know, these are examples like the piecewise linear minimization, Chebyshev centering. These are sort of, it should be giving you a hint that a stupid problem family like linear programming that's been around since Fourier, right, was fully understood by Gauss. Actually, I don't know that, but it would appear to be a safe statement, since everything, I think, was fully understood by Gauss. But that what's cool about it is that this kind of very innocent-looking, boring thing that, you know, if you go to the OR department, you know, you'll find out about diets and some other stuff. And what's cool is it actually has lots of applications, and a lot of them are not, you know, they're not obvious things, right? I mean, it's not obvious that finding the biggest ball that fits inside a polyhedron is a linear program for the reasons I mentioned before. So anyway, so that's, we'll quit here. I should remind you that at 11 today, we have the section that would have been yesterday.